Hello, everyone. So I'm going to present my work about the thread-based resistive sensor for tactile and slippage detection in smart bionics. So before we delve into the bionic world, this will be my content. I'll give a brief introduction, the problem statement, a little state of the art, what are the challenges and research gap in the technology, and what is the solution we proposed and implemented, and I will conclude with experimental results. Before we delve into the bionic world, let's first acknowledge the magnificence of human hand. I mean, it is the marvelous creature of mankind, how human hand can perform manifold functions from a gentle touch to integrate movements. I mean, it's immense, it's of immense magnificence. But unfortunately, for amputees, due to the loss of the hand, there is not only just the sensory and motor deficits, but also it's associated with low esteem and a sense of being mutilated. But as researchers, we are driven with the belief that the cutting edge development in the bionic arms can cater to all these problems and give an intuitive and a sense of embodiment to the prosthetic arm and hence make the lives of the amputees easier. So let us first understand how we are able to mimic the slippage detection in prosthetic arms. So human tactile system is the richest tactile system, as we know that our glabrous skin is constitutes these thousands of mechanoreceptors which are sensitive to the mechanical variations or the interactions between the object and the skin. And these mechanical variations are transduced into action potentials and transmitted to the brain through central nervous system. So in an attempt to mimic this behavior, we are trying to incorporate sensors in the human bionic arm. And in place of the mechanoreceptors for transduction, we're using, for interfacing circuits we are embedding the electronics. And then these electronic circuits convert these mechanical variations into the electrical signals, which can be later conveyed to the brain, like in the form of a sensory feedback, or can directly given to the prosthetic motor control drive to adjust the grasp. So this is the idea behind the biomimic slippage detection that we are implementing. And the need of the slippage detection is obvious. It's pretty obvious because of the increasing functionality, adaptability, and intuitive control. Obviously, for handling and to avoid any mishaps, we are doing this. So a little bit of the literature, we have been using force sensors and pressure sensors for the slippage detection. These force sensors are primarily the piezoelectric and resistive based FSRs, but due to the temperature and hysteresis behavior, they have some disadvantage. Again, the computer vision technologies are helping us for effective slippage detection, but there are many image processing algorithms that we can use to visualize the interaction between the surface and the object and accordingly detect and anticipate the slip. But they are computationally expensive. So moving on to the texture surface sensors, they again detect the variation in the surface texture and can help to anticipate slippage. Machine learning algorithms are augmenting these sensing technologies considerably, and with the pattern recognition techniques, etc., aiding for the slippage detection from the sensors data. And finally, the feedback systems are also augmenting this technology. The haptic feedback or the artificial sensory feedbacks are integrated to give visual cues or even the haptic feedback for slippage detection and mitigation. primarily we are facing the challenge as shown in the slide. But one of the most crucial challenges that we are facing in the slippage detection is the static and dynamic specificity. So this is related to the instant of the initial object contact when we hold the object, and then the slippage phenomenon actually. So the static measurement is with regard to the initial grasping of the object, where the sensor may feel the detection change in the force and then can give an false alarm of the slippage. And the dynamic measurement is with regard to the actual slippage phenomena. So we want to differentiate these two events. So most of these current sensing technologies do not have the specificity to the static and dynamic measurements. So it is one of the most critical aspects of this challenge, and we are currently, our sensing approach is giving a potential solution for this. Again, the sensitivity, feedback time, computational complexity, the cost and sensor integration, these are another challenge in this regard. So we're using a thread-based sensor. Since the thread-based wearable sensors are gaining quite a momentum lately because of their simple design, high sensitivity, cheaper cost, durability, and ease of integration. So we've used this a very simple thread that is probably you would have seen like in the face masks, the thread that goes in, around the air. So we're using the same elastomeric thread. We are coating it in carbon ink, so to give it the conductivity, and then we are using some PDMS material to avoid the ink to flake, and then finally we heat it in an atmospheric oven for around 20 minutes, and the sensor is ready for resistive measurement. So this sensor is basically, it is sensitive to the different types of forces, the compression force and the elongation force. So we exploit this this feature to provide a solution for the static and the dynamic measurements that I was talking about. So this is the proposed interfacing circuit. We're using a simple Wheatstone bridge configuration where we are replacing the two resistive legs with current source. We have a constant current source, LM334IC we're using as a constant source IC, in which the external resistance is changed to give a required amount of current. And we are using a reference resistor R that is equivalent to the base resistance of the thread resistor in the other leg, the thread base. In our experiment, we used around a 7 kilo ohm as a reference resistor in accordance with the thread-based resistor sensor's base resistance. And then we are using a simple INA 126. So it gives the difference of the voltage Vs and Vr. And hence, this configuration will give primarily better resolution, sensitivity, high PSRR ratio. So all these features thanks to the current bridge excitation. So the experimental results, first of all, let's see how our sensor mitigates to the static and dynamic characterization that I've claimed in the starting of the presentation. So when the thread, first we are going to emulate the behavior of the object contact, the initial object contact. So when we are trying to grasp the object, so we apply pressure in the normal direction of the thread. And since the thread has some fibers and these fibers have some gaps in between, and when we apply the pressure in the normal direction, these fibers kind of come closer and there are more conductive paths, and hence a decrease in the resistance. So this decrease in the resistance is manifested in a decrease in the voltage of the INA. And we can see the voltage going in the negative direction in the graph. So it is related to the static characterization of the touch, that is the initial contact. Then we see while we are emulating the slippage behavior, we are elongating the sensor, and it gives an effective increase in length of the sensor, and hence the resistance increase and the voltage increase. So the slippage phenomena, as you can see, is attributed by a certain increase in the voltage. So there are some high frequencies in a stable position and then some low frequency component. So these two are quite differentiable, and hence the potential solution for the problem. So this is the result, how the output changes with the change in length. So the first graph shows the slippage behavior while we are increasing, where we are changing the length, we are sliding on the thread, and how this length is. It gives a good resolution and a good sensitivity, as you can see from the graph, from the slope of the graph. And the another one is response to the tactile or the touch stimulus to the thread, where the displacement is basically a manifestation of the force that we in our experiment use a mechanical strain gauge. So the displacement is basically the manifestation of that force and or the pressure in the normal direction, which can be like quantified by the Hooke's law. So this is in response to that initial condition of object contact. So to sum up the objectives of the work, we have developed a simple, low cost, obviously, because it's quite just a thread dip coated in carboning. So quite affordable and flexible and durable force sensor primarily. And it shows excellent selectivity to the static and dynamic measurements, as I've explained. And since in the circuit topology, we have used the current bridge resistance measurement, so it promises high power supply rejection ratio, since we are using a current source excitation. So it is independent of the fluctuations in the voltage supply. Baseline resistance compensation has been met, and the sensitivity and resolution quite considerable. Thank you, that's all.